Hi everyone. So this is a joint work with Laurent Massoulier, my advisor, and Dawn Tosley. So behind the esoteric title is simply a graph inference problems, which means that we're trying to find a planted structure inside some graphical data, usually a random graph. So the main example, which you've probably heard about, is the planted clique, but there is also the stochastic block model or more exotic examples such as the planted Hamiltonian path. And both the planted clique and the stochastic block model are examples of low-rank inference problems, which means that the planted structure is seen as a matrix, low rank. For example, you can see that there is a decomposition of the adjacency matrix of a stochastic block model into a rank 2 matrix, except for the diagonal, and some random noise. So a natural question could be what happens when the structure is not low rank, which is the case in our model. So our setting will be, instead of doing like the planted clique, which is planting a dense subgraph inside a dense graph, we are going to be planting a sparse subgraph inside a sparse graph. So more specifically, the underlying data under the null hypothesis, we simply observe an Erdős-Rényi graph, so with parameters n and lambda over n, so it's a sparse random graph. And under the alternative hypothesis, we observe the union of this random graph G with a fixed graph gamma, where we have randomly selected the vertex set that supports gamma of size k, which will be our main parameter for estimation. And the two cases for gamma we will consider here are when gamma is simply a path of length k or a complete DA tree of height h. So the goal here is twofold. First, detection, which means that we want to be able to discriminate between the null and alternative hypothesis with high probability to tell the two hypotheses apart. And then reconstruction, which is once we know we are in the alternative hypothesis case, we will aim to recover at least a fraction of the vertex set of the planted subgraph. This is usually, but not always, a harder problem than detection. And our measure of success for this is called the overlap. It's the overlap of an estimator is simply the expected value under the alternative hypothesis of the intersection between our estimator and the ground truth. So the results we've been able to get for the planted path are as follows. First, it's pretty obvious that the results have to depend on the mean degree lambda, since when lambda is less than 1, the graph is subcritical and is completely disconnected, so there is no path of length a lot more than log n. And indeed, we proved that the actual threshold is log n times a function of lambda. And under the threshold, both detection and reconstruction are completely impossible, while they are easy, which means that there are polynomial algorithms that can perform the task correctly, above the threshold. The more interesting picture is in the supercritical random graph, so when lambda is more than 1, because a simple edge counting argument shows that detection is easy above when the k is largely above square root of n. And an estimation can show that detection and reconstruction are both impossible when k is well below square root of n. But the interesting tidbit is that reconstruction is actually completely impossible whenever k is much less than n, which means that there is no estimator that can achieve overlap which is not smaller of k. So we can hope to recover even a small fraction of the vertices. On the other hand, for the planted DA tree, we have a similar dependency on lambda, but the critical value lambda d is not 1 anymore, it depends on d. It's actually the critical value for emergence of the d-core in random graph theory. And here we chose as a parameter the height h of the tree for simplicity of results. For lambda, for supercritical graphs again, we haven't been able to find out much because the methods we used for the path are fairly specific and do not apply to this case. However, when lambda is less than the critical value lambda d, we showed that there is a critical height, which is roughly log n, where log is in base d, where below this threshold, detection and reconstruction are again completely impossible, and above it, detection is easy. However, we also proved that complete reconstruction is always impossible as long as the height is less than log d to n, which corresponds to a k much less than n, and that's because the leaves of such a tree make up a positive proportion of those vertices, and they are actually hard to recover even if we know the first h-1 levels of the tree. So it's impossible to have an overlap of roughly k. So why are those results interesting? That's because in most studied inference problems, such as the ones I mentioned, the planted clique or the stochastic block model, the phase diagram is always roughly the same. There is first an impossible phase where detection and reconstruction are completely information theoretically impossible. Then there is a hard phase where both are theoretically possible, but we don't know of any polynomial algorithms that can perform this task. And then there is the easy phase where we know polynomial algorithms that work for both detection and reconstruction. However, in our case, we have several interesting properties. First, there is absolutely no computationally hard phase, which means that as long as we prove that detection or reconstruction are possible, then immediately we have polynomial algorithms that can perform this task. And secondly, we prove the existence of a phase where detection is easy and reconstruction is either partially impossible in the case of DA trees, or even completely impossible in the case of planted path. So we hope that this kind of behavior can help broaden the topic of inference problems on because it can extend the field of such inference problem. Thank you all.